Hello, everyone. My name is Radu Emanuel Cișcariu. I'm a security research engineer at XE Application and Threat Intelligence. This is my second time here at DefCamp, and I'm hoping that everyone has as much fun as I do. For today, I'm going to have your attention with one of the projects that I've been working at this year. So, as a security researcher, one of my tasks is to investigate vulnerabilities in different kinds of application. Some of them have proof of concepts attached to it. For example, some of the vulnerabilities have an exploit published on ExploitDB. Everyone knows about ExploitDB. And if you want to tamper with that exploit, you can simply take the exploit, download it, install the vulnerable application, and have fun on your own and see what's going on with that application and with that vulnerability. But what do you do when you do not have a proof of concept, an exploit for it? Moreover, what do you do when you don't even have the application, the source code available? How do you investigate those vulnerabilities? The aim of this presentation is to give a full walkthrough, a comprehensive walkthrough on how would you go about investigating these exact cases. But before that, some words about the Windows security ecosystem. So how many of you heard about Bluekeep? It's a more recent one. Please raise your hand. A lot of hands. Why are you smiling? What about Eternal Blue? This is the older one. Okay. There's clearly a lot of interest for Windows application and Windows services, and a lot of security researchers, independent or working at the company, or even people that are trying to do bad stuff, are looking into them. Only this year, a recorded feature, which is a threat intelligence provider, come up with this report that the top 10 most exploited vulnerabilities from the past year were vulnerabilities actually targeting Microsoft Office. To convince yourself of that, you just have to go on the CVE details and take a look at the number of vulnerabilities that were showing up in the Microsoft products. For example, in 2017, more than 700 of them, and this year, about 700. So it's clearly a lot of interest. What's happening when the Microsoft Research Center or developers working there are discovering a vulnerability? Well, after they release a patch, they also give away a security advisory that contains generic information. For example, what kind of vulnerability is taking place there? Maybe it's a type confusion, maybe it's a buffer overflow. What is the actual component that is vulnerable? For example, it's a service, or it's GDI, or it's something else. They also give a link, obviously, to the patch, and you can download it, and that's pretty much it. You don't have many information to start with if you want to investigate such a vulnerability. So I started looking at the vulnerabilities that were showing up in Microsoft products this year, and a whole lot of them started to show up in GDI. As I didn't know anything about the GDI whatsoever, I got curious, and I started looking into a certain one of them. GDI stands for Graphics Device Interface. It's a Windows component that allows you to render fonts and draw shapes and handle palettes and so on. Its job is not to render Windows forms. That's taken care of by another Windows component, which is called User32. GDI provides an application programming interface which you can use to do these kinds of operation. You just have to grab a handle to the window, which is called device context. Then you will just do different kinds of operation, and that will get displayed on that specific window. For example, you can draw images, you can do rectangles, you can display fonts, as I said. What happens beyond the API? Let's see. So this is an oversimplified architecture of the GDI component. On one side, on the user mode, we have the user mode GDI. This has been around since the beginning of Windows. It provides you an API that you can use in order to do this kind of operation. Starting with Windows XP, an extension to the original WinGDI has been introduced. This is fully developed in C++. Its name is GDI+, and it's kind of an extension of the original WinGDI. It provides support for different image file formats, such as proprietary Windows file formats, enhanced media file formats, or Windows meta file formats. And it can also give you the ability to do different kind of graphic operations. So when you're doing an API call, that gets handled by the kernel mode, the win32k.sys. And that acts like a router, which will send the request originating from the API to the actual driver that will do the heavy lifting. And as you can see, the drivers are placed in the kernel mode. And this is by design. Starting with Windows NT, Microsoft decided that it's a good idea to move the kernel drivers from the GDI drivers from the user space to kernel space. They said that they did that in order to improve graphical performance, and no security implication will happen whatsoever. It's a funny article, you can read it. But there is a security implication, because if a certain graphic operation is done in the wrong way, and if it's vulnerable, then this can lead to a weird case of privilege escalation, of course. Let's try with both hands. And the attackers saw an opportunity in this situation. And as a result, they started looking into the GDI, and it turns out that a lot of vulnerabilities in Windows GDI were using malware campaigns. And if you're thinking that GDI has been thoroughly investigated, then you are wrong, because only this year, more than 30 vulnerabilities were affecting graphics device interface. So how can an attacker abuse such kind of vulnerabilities? Well, there are a lot of clients, obviously. GDI is a very important and fundamental module to Windows. For example, Microsoft Office is using it. You can insert proprietary Windows file formats, for example, enhanced media files or meta files, and that will get rendered using this module. And so if the module is vulnerable, then this is your attack entry point. Or you can use a browser. You can attack via this way. You can insert a certain meta file into a JavaScript, and that will get parsed using the vulnerable module. And again, it's pretty much game over. And Adobe Reader is using GDI, Edge as well, so there's a large attack surface. As I said, I started looking into GDI vulnerabilities, and I've just picked one of them at random. Again, after investigating and looking at the security report provided by Microsoft, you don't have too many information. I just know that it's a critical heap overflow vulnerability, and it could lead to remote code execution in certain scenarios. I also know that it affects GDI plus.dll, and after I've done a little bit more investigation, I have stumbled upon a ZDI, a Zero Day Initiative report, that gave me this another critical piece of information, that the vulnerability is located within the method that is named doRotated stretch BLT. This turns out to be a very useful information in the investigation to follow. Of course, there is no POC, otherwise this presentation will have too much sense, really. Okay, so what can you do? Well, usually you start with patch diffing. Patch diffing is definitely not a new technique. It has been a while since it was employed for the first time. It basically allows you to compare two different executables at the basic block level. And it allows you to look at the differences and understand what has been patched and how it has been patched. So it's a very useful tool, because not only that you can inspect the patch, but if you look at the target enough time, then you can gain insights about where are the critical locations within that application where the problems arise. And also, how is the development team targeting and deal with these kinds of issues. So a lot of people are using BinDiff to look in a lot of applications for a larger amount of time. How would you go about patch diffing? Well, there are certain steps, and they're pretty straightforward. You will take 2 consecutive patches. When we're talking about Windows, these patches are really cabinet files, and cabinet files are fully fledged zip archives. You would extract those archives, and you take the file of interest from them. Then you import those files in IDA and let IDA run its initial analysis on both files. Then you would run the bindiff plugin. Bindiff has a plugin that allows you to integrate it with IDA, and we'll do exactly that. We'll compare those both files at the basic block level. And you will start. It stopped working. 1 second. And you would inspect the differences. So this is exactly what I have done. I've taken 2 files. What you want to do when you do patch diffing, try to find 2 files that are very close as a version 1 to each other, because you want, obviously, to limit the amount of code that you want to look into. Import them in IDA. IDA will run analysis. Then you start the bindiff plugin, and lo and behold, this is the output of the actual bindiff. So the important columns that you want to look at is the similarity column, confidence, and primary and secondary name. Primary and secondary name will give you the names of the functions that have certain differences in them. And as we can see, our method is located there, the rotated stretch BLT, which is a good sign because it means that we have the right files and we're comparing what we have, what it has to be compared. Okay, so we are seeing that it's a pretty big difference, like 96%. And let's start investigating what the actual issues are. Okay, so bindiff also has this interesting functionality that it allows you to see both methods, the vulnerable and the patch one, side by side at the basic block level. And you can get a hunch where the actual vulnerable code, the actual differences in the code are. So let's zoom into that part where there seems to be some differences and find out what happens there. Okay. So these are the functions, the patched one with green and the vulnerable method in the unpatched DLL with red. What do you think that the issue is? So my first hunch is that there is a classic case of memory corruption because of the unsafe memcopy operation. So what can we do with this? Well, if we somehow can gain control of the source buffer and the size that will get copied into the destination buffer, then we will produce an overflow to the destination buffer. That will hopefully overwrite some structures in the memory, such as SEH, structure exception handling on Windows, or some other code pointers. And by overwriting that, we can obtain the control of the EIP, the instruction pointer, and hijack the control flow of the application. Let's see if that is indeed the issue by looking at the patched code. Damn. Okay. This is the patched code. So they indeed added a form of sanitization before the memcopy operation. They are looking at the size, and if that is bigger than a certain amount, then the destination buffer is going to be allocated with that exact size. So now the source buffer and the destination buffer are of the same size. So this seems okay to me at the first look, but what happens if we make an allocation make a big allocation? I mean, maybe the size and the destination buffer, the source buffer are still in our control, right? Maybe we can somehow bypass this patch and make a great allocation and create a denial of service condition because we do not have an upper limit. How much can we allocate really? Is this a blunder from the Microsoft team? Well, it turns out that it isn't a blunder. They've included a method in the patched DLL, which is called sanitize and expand buffers. And the method does exactly that. It kind of takes care of the allocation and makes sure that they are made within certain boundaries. So we cannot really bypass the patch, and everything seems okay so far. But at least we know what the issue is. So what can we do now? What can we do with this piece of information? We know that there is that it can lead to remote code execution, and we see that we can gain somehow control, but we need to find a way to reach that certain piece of code. And IDAP offers you this interesting functionality, which is called X references to, and this practically allows you to see all the methods that will eventually call the method of interest. So at the base, we have our vulnerable method, and what are in the top of the tree are the method that may be interesting to try to invoke in a certain way. So after I have investigated each method, it turns out that they are not external methods. So there is not a direct API that we can invoke that will lead to one of those. So we kind of have to continue with our investigation and go further with the reversing. So I've noticed that all these methods have a certain name. They seem to be handlers for something. So I've started wondering they're handlers for what exactly? It turns out that they are handlers for a specific Windows proprietary file format, which is called EMF, Enhanced Media File. So Enhanced Media File is nothing really than a representation of a graphical image. And how this representation takes place? Well, let's say that we want to draw a rectangle, that it's filled with the green color, and it's rotated like 45 degrees to the left or to the right. If you want to represent that in an EMF file, then we'll have a record for the rectangle, for the polyline, then we'll have a record that specifies the green color, and then we'll have a record that specifies the rotation operation. So we have 3 records chained together, and that's everything that there is to enhanced media file format. So it seems that there are records that have to be handled somehow. And I started thinking that these handlers have to be in there, in the DLL. So I've tried to see if they are grouped somehow. And it turns out that all the handlers that we see earlier in the call tree are practically indexes in an array. And the array is called, okay. Do you have another one? And the array is called the drawing orders. And right now we have to somehow trigger these handlers. So we continue with our investigation. How can we trigger a drawing order operation? Again, we inspect the DLL. Okay. If we inspect the DLL, we can see that the drawing order operation is going to happen if this method is called bparse win32 meta file. Still not working. It's not working. Maybe if I go this way. Okay, seems to be better. Okay, so this is the method that eventually call the drawing order array. In this method, bparse win32 meta file, we have a reference to that array that contains the whole drawing operations. So now what we have to do is to find a way to call this method. Again, we make use of the X references to IDA functionality. So at the base is bparse win32 meta file, and it seems that well, it's not working. This method, EMF to VMF bits, will eventually call that method. And after I've taken a look at this method, it turns out that is an external one. So we kind of have our target. But let's make a summary of what we have learned so far. So the bparse win32 meta file will call our vulnerable method, rotated stretch BLT. But this will only happen if we include in the file that we are serve as input a specific record, stretch BLT record. Okay. Damn, this is not working. So I need to find a way to call this method, and I know that it's external. So now what do? I take a look at the Microsoft documentation. And it turns out that this method, bparse win32 meta file, is actually a part of the meta file class. So I do have a way to make an API call, and hopefully that will reach the vulnerable code that is of interest for us. So let's try to do that, if this thing will let me. Okay, so what is our hope here? We are trying to make that call, the API call, DMF to VMF bits, to call our vulnerable method and produce a crash. And I started thinking, how was this vulnerability discovered? Well, as you could see earlier, there were a lot of methods that did in turn call other methods, and they had a lot of arguments. And this pretty much seems it's a good indication that the vulnerability was found with fuzzing. So what I've tried to do is I've tried to kind of reverse fuzzing this vulnerability and try to come up with a crash for it. Let's see how that went. So fuzzing is about coming with interesting inputs, and we are hoping that interesting inputs will lead to a crash and to a situation that the developer didn't handle correctly. And it's useful both for the security researcher and both for the developer. There are multiple ways to classify fuzzing strategies, but the one that I like the most is evolutionary-based fuzzing versus generational-based fuzzing. Evolutionary-based fuzzing is about using genetic algorithms in order to create a better code coverage. So you're hoping that the genetic algorithm will use mutation strategies, and those mutation strategies will lead to better coverage. On the other side, we have generational-based fuzzing. And this is about coming with a grammar for that specific input that will give the fuzzer some kind of input awareness, and hopefully that will reach further into the code. It will find more interesting behavior. For my investigation, I've chosen the WinAFL fuzzer, which is a tool built by Google Project Zero. It is actually a fork from the original tool created by Michael Zalewski, a Google security researcher, AFL. So, as you've heard earlier in Alexandru Căciulescu's presentation, is the tool to go when you're trying to find vulnerabilities, and it has a huge trophy case. Okay, now I will give some tips for using AFL in case you want to start tampering with it. First tip is to understand the target. Really take a lot of time and look at the ways that you can use that API. For example, if you're fuzzing an API, look at the source code, look at the examples. Some of the application also provide the tests for it, and that is a good place to look at when you're trying to understand what you can fuzz. And try to concentrate your efforts at first at conversion operation, at initialization, and so on. Another tip would be to come up with small samples that you would feed the fuzzer at the beginning, because you want your fuzzer to be as fast as possible, and if your initial test case is big, then the processing will take a larger amount of time. And that will slow your fuzzer, and you don't want that. But also you want a lot of samples that will create a larger coverage initially to make sure that you have a lot of places to start looking at. Another thing that you can do is to run the fuzzer from the RAM disk. That will allow the fuzzer to read the samples directly from RAM. and it will deny the overhead produced by reading them from the disk. And you can also make use of the master-slave feature that AFL provides. If you start multiple instances of fuzzing in parallel, then the slaves can communicate with the master, and they can communicate and exchange fuzzing strategies, and that will create a better coverage in a faster amount of time. Use a dictionary. A dictionary is a way that you can instruct the fuzzer to use certain strings to insert when the fuzzer is trying to use mutation strategies. An even better strategy would be to use AFL Smart, which allows you to specify a grammar, and this will hopefully provide a better coverage in a faster amount of time. Another thing to look at is you have to watch the coverage. So the coverage is an asymptotic curve. At a certain point, the coverage will not become as big as fast. So when the coverage starts to slow down, you won't get a certain amount of increase in a smaller amount of time. You'd want to stop the fuzzer and come up with new samples and new fuzzing strategies. Okay, so let's set up the fuzzing campaign. We have to write a harness, which is essentially a piece of code that makes the call to the actual API that we saw earlier through our reverse engineering phase. Then we have to provide instrumentation in order for fuzzer to know what the coverage is. There are multiple ways that you can employ instrumentation in Windows, but the one that I have used and I'm familiar with is DynamoRIO. DynamoRIO is a runtime instrumentation framework, and what this will do, it will insert certain opcodes at runtime into the binary that is running, and that will inform the fuzzer about the code coverage in that situation. And if that specific sample that you give it at input will provide a better coverage, then AFL fuzzer will know that that is the right mutation strategy and will enforce that further on. You also have to come up with test cases. So we have to come up with initial EMF files that the fuzzer will use and will start investigating. We also have to set up the fuzzer and start fuzzing. Let's see how that goes. So this is the harness. At the beginning, we have to open from the command line the file, and after that, we'll make the API that we discovered earlier, found in the Windows documentation. After that, we have to generate the initial samples, and again, we can make use of the GDI, Application Programming Interface. As we saw earlier, our vulnerable method has a chance to be called only if we provide a certain record type, and we will create our files in such a manner that will include such a record. Another thing that you want to do when you're doing fuzzing is to try to limit the number of samples that you're feeding the fuzzer. If you're not doing that, and if the samples are pretty similar, then your fuzzer will waste useful CPU cycles on samples that are not contributing to the code coverage very much. And there is a tool that allows you to do exactly that. You will take each sample, and you would look at the code coverage that it produces. And if the code coverage is similar for 2 consecutive samples, it will eliminate those from the initial corpus. So from initial 32 test cases that I come up with, using this tool, I have only 15 samples left. Okay. So after I've started the fuzzer, I have waited a day and a few more hours, and it seems that my fuzzer is behaving pretty nice. I already have more than 80 crashes, and the speed is pretty good. So I'm happy about those crashes, and I want to investigate them. And after I have seen that the coverage isn't increasing very much, I have decided to stop it and investigate the crashes. The fuzzer behaved so well that my antivirus thought that the generated crashes are malware. When I started triaging them, the antivirus started complaining, and it gave these pop-ups that I have infected with Bloodhound. So this would be an interesting research, how to foil Windows signature using genetic algorithms. After going through the crashes, one of them grasped my attention. It turns out that it is in the exact same method that I was trying to investigate. So this might be a possible valid finding. So I took this sample that the fuzzing campaign produced it, and I started looking into it using the debugger. So as you can see, the call stack is pretty big. No way a security researcher could go through such a large amount of code in a small amount of time and come up with this just by code analysis. So probably the vulnerability was found using fuzzing. Another thing that you can observe is that the crash produces in the exact same place as we've seen in the disassembly after the memcopy operation, right? So this is a valid finding. There is this plugin for a Windows debugger, which is called exploitable. This essentially looks at the memory state after the crash produces, and using certain heuristics, it declares whether if the vulnerability is exploited or not. You can use this plugin to make your to make a better triage of the crashes. When I've started my fuzzing campaign, I've decided not to look only for this specific vulnerability. So I've tried to come up with an initial test case that would produce as better coverage as possible. So I used different EMF files with different type of records. And looking through the crashes, I've observed that there are crashes that were produced in different libraries and for different methods. And it turns out that some of the methods some of the crashes were correlated with other CVs as well, with other crashes. And there were 5 more crashes that I couldn't correlate with anything else. So I've decided to send those crashes to Microsoft. And they assigned to null pointer the references bugs for those findings. 2 of them were valid. I've also put the harness function that I've used for fuzzing online. You can find it on my repository online. And you can go ahead and try some fuzzing on your own. For more details, you can contact me on Twitter. This was my presentation, and thank you for your attention.
Any questions from the audience?
Hi, so you said future work, more fuzzing. What targets do you have in mind? What do you want to achieve more specifically?
Oh, I have a lot of targets, believe me. Trying to fuzz the JavaScript engine of Edge, of Firefox. I'm working with my colleague Daniel, and we're trying to come up with a fuzzer now. We have a lot of projects in mind.
Any other questions?
Hello, congratulations for the speech. The first question, do you research only Windows?
No, I'm looking into different kinds of vulnerabilities from other products as well, but recently I got acquainted with Windows vulnerabilities and I want to get better at investigating those. So,
The second question, can you tell us more about a past research like this?
you mean my research?
Yes.
We can take this off the scene and discuss. I have a lot of resources to share. If anyone is interested, please reach to me. I actually had a hard time putting together all the resources out there on fuzzing and tried to come better at this on my own. So if anyone knows more about it, please reach to me and we can discuss it further.
Thank you very much.
Thank you.
Any other questions over there?
Hi, thank you for
Hello.
your presentation.
Thank you.
GDI Plus library is used only in Office or it's used in general in...
Well, you know, GDI clients can use both WinGDI and GDI Plus interchangeably. There's no rule for that. You can use any of the exported functions. But from my knowledge, Microsoft Office employs most of the, generally only GDI Plus methods because they are optimized for a better rendering speed. Thank you.
Any other questions?
Hi.
Hello.
I have a simpler question. Did you try exploiting these crashes as well?
Oh, I'm not that good yet. Actually, I'm the level of exploiting structured exception handling structure. I mean, those kind of overflows.
All right.
So I'm at the beginning.
Okay, thanks.
We had one there? No? All right.
Do you know if you can use fuzzing for anything other than buffer overflows?
This is quite a good question. You can, in general, you can use fuzzing only to find issues that will lead to memory corruption. But there are ways to find other vulnerabilities. For example, you can find type confusion bugs. Or you can use, for example, on Linux, you can employ different sanitizers. For example, address sanitizer, SAN, or undefined behavior sanitizer, which what this sanitizer essentially do is they will crash the application when a certain kind of bug is happening. And so if you're compiling your application using this sanitizer, you have a good chance to find other vulnerabilities as well, because eventually the application will crash and you can start from that point onward.
Are there any questions left?
My question is, did you find any kernel vulnerabilities in
Sorry?
your research? Did you find any kernel vulnerabilities in your research?
No, these were only user space crashes.
Thank you.
Thank you.
All right. If there are no further questions, spoke too soon.
My question is, at some point you have to look at the coverage for your fuzz binary to see if you're making progress. Do you have recommendations for tools that let you see visually where your coverage is expanding into the binary?
AFL provides you multiple scripts. Then you can actually see the evolution of the coverage in a graphic. So you will see the exact curve, the exact asymptote being drawn. And you can just take a look at that curve and decide when to stop. At a certain point, the fuzzer will not make any progress. And
okay. I was thinking of being able to see which functions in your disassembly are being hit and which are not.
oh, there is a nice tool for it. It's called Bug ID. It's an open source tool. What this tool does, it's an IDA plugin tool. It's an IDA plugin, and you will take the samples and you would run them through Bug ID, and it will tell you essentially what is the degree of coverage and for what method. So it does exactly what you want. Check out Bug ID, and it's what you need.
All right. Thank you, everyone. Thank you, Radu.
Thank you.